Okay, so my name is Martin Takacs. I will be chairing the next two sessions. So the first speaker will be Ji Xu, and he will be speaking about approximate message passing.
Okay, I will begin. Today, I will talk about approximate message passing for amplitude-based optimization, a new algorithm that's designed to solve the phase retrieval problem. It's a joint work with Junjie Ma and Aaron Malaki. So first, what is phase retrieval? The task of the problem is to recover an n-dimensional signal x star from its n-faceless linear measurements y. Mathematically speaking, we have y equals to the absolute value of linear transformation of the true signal x star plus a random noise. Here, the true signal x star is a complex vector with ID entries following a known distribution px, and the measurement matrix A is a complex Gaussian random matrix, and finally, the random noise W is an ID Gaussian noise. Now, this model has many applications, one of which is the X-ray crystallography. That is, the goal is to detect the 3D structure of an object of interest, which usually is the molecule. More specifically, let's look at this figure. We will illuminate the object of interest, which is the molecule over there, and by the X-ray. And then over there, we have a screen that can collect the intensity of the diffracted rays. So in this example, the diffracted X-rays can be considered as a linear transformation of the true signal x star that contains the structural information of the molecule. And since you can only collect the intensity of the diffracted rays, there goes the absolute value included in the model. And our best hope is to recover the signal up to a global phase. Now, besides this example, we can also name many other applications, such as microscopy, astronomy, optical imaging, and etc. Due to its popularity, many algorithms that aim to solve the phase retrieval problem have been proposed and been analyzed, like these. To know that, there are two main types of algorithms. The first one is the vertical flow and its variance, and second one is the amplitude flow and its variance. So let me briefly introduce what are these algorithms and known results for their performance. So first, let me talk about the amplitude flow. In this approach, we formulate the phase retrieval problem into the following optimization problem, where the loss function is known as the amplitude loss. Note that this is a non-convex optimization. So a typical approach is to use iterative search algorithm with certain initialization. And indeed, in this amplitude flow algorithm, we start with the initialization step where we pick the initial to be the leading eigenvector of the following matrix D, where different choice of function T give different variants of the algorithms. This initialization step is also known as the spectral initialization. It can provide an estimate that is non-orthogonal to the true signal x star. Then, for the main body part of the algorithm, we will refine the initial estimate by local search algorithms such as the gradient descent. So this concludes the whole structure of the amplitude flow algorithm. On the other hand, the same algorithm has been applied to vertical flow and its variant as well, except that we replace the loss function by the following intensity loss function. And as you can see, it is also a non-convex optimization. So since both approaches has been non-convex, so do we have any theoretical guarantees for the performance of these algorithms? Well, the answer is yes. The current analysis has shown that if we consider the MSE, the mean square error, then in the noisy setting, if we want MSE to be 0, which is a successful recovery, then the sample size n should be at least proportional to the dimension n. And in the noisy case, if the sample size is at least proportional to the dimension n, then MSE is at most the same order as the variance of the noise. However, I have to point out that different algorithms may correspond to different constants, and none of these analyses have shown what are these constants. So I may want to ask the question that, can we specify the constant C for an algorithm so that we can compare the performance among different algorithms? And also, I want to ask, can we characterize the performance of the algorithm exactly under the presence of noise? And since the algorithms I have listed are all iterative algorithms that require an initialization procedure, and I have to point out that for amplitude flow and vertical flow, the initialization is required to be close enough to the true signal x star. So I want to ask, what is the impact of the initialization scheme, such as spectral initialization I had described before? Well, we are not able to answer these questions for amplitude flow or vertical flow yet, but we are able to answer these questions for the new algorithm, which I will talk about today, approximate message passing for amplitude-based optimization. But before I talk about approximate message passing framework, let me first introduce a slightly different formulation of the problem, such that it has some advantage over the old amplitude flow approach. That is, we add the L2 regularization to the amplitude loss. The idea is to avoid bad local minimum by this regularized optimization and to provide an estimate that is more appropriate initialization for the original optimization. So this technique is also known as continuation. So let me use a figure to illustrate this. Suppose we want to minimize this function fx. As you can see, we have a global optimal, which is u, and a local optimal, which is v. Now suppose we have initialization x0 over here. Then by usual local search algorithms such as gradient descent, we probably will end up in the local optimal v instead of the global one. However, if we add a large enough regularization term, such as the orange curve over there, we set mu1 equals to 20, then even start at the same initialization x0, we can end up in a better estimate, which is x1, where the shape of the original loss function fx has become much nicer. And if we look at the region around x1, we can use x1 as an initialization for even smaller regularization parameter, which is mu2, and apply the iterative algorithm again and get the better estimate, which is x2. And again, we can use x2 as an initialization for even smaller regularization parameter, mu3, and eventually we can get to the global optimum, which is u. So to conclude, the continuation idea is the following. We pick a sequence of regular parameter, mu k, such that it is decreasing to 0. And then the solution of the current optimization problem will be the initialization of the next problem. This can provide, sometimes can provide a better estimate comparing to directly solving the original optimization problem. Now finally, the iterative algorithm we use here is the approximate message passing. So what is the approximate message passing framework? Well, in short words, it is an iterative algorithm derived from belief propagation or message passing. In our phase retrieval case, the exact algorithm, or I also refer as AMPA, is defined by the following. So the sequence xt is the estimate for the true signal x star, and the second sequence, pt, well, the absolute value of pt is the estimate for the measurements y. Now, for those who are not familiar with AMP framework, if you ignore the red term over here, then the whole algorithm can be considered as a variant of the gradient descent, while the blue term comes from the regularization term. Now, for the red term, which is also referred as the oscillator term, it intuitively cancels the correlation between the measurement matrix A and the estimate xt. And therefore, it can reduce the bias caused by the correlation between each iteration. And further, I have to point out that like many other AMP algorithms, in each iteration, the calculation is inexpensive. So the whole algorithm is computationally efficient. Now, you recall that I have raised these three questions in the beginning of my talk. And for the next few slides, I begin to answer the first question. That is, not only I want to show that AMPA works as long as the sample size is at least proportional to the dimension, but also I want to characterize that constancy exactly. To do that, let's consider this asymptotic framework, where both sample size m and dimension n go into infinity, while the ratio m over n is fixed to be delta. Then a appealing property about AMP framework is that the asymptotic behavior of the AMP estimates can be characterized exactly via the state evolution platform. That is, if the initial x0 is independent of A, then at t iteration, the estimate xt is approximately a scaling times the true signal x star plus a complex Gaussian independent random noise. Now here, the scaling of alpha t and sigma t square can be tracked by the following deterministic update rules, which also refer as the state evolution. So, the convergence of xt can be converted to analyze the convergence of alpha t and sigma t square. Now the question is, where do they converge to? Now, the answer will be, it can only be the solution of the following two equations, which is also known as the fixed points of these equations. To simplify these, let's first solve alpha from the equation 2 for fixed sigma. Then we can get alpha equals to, absolute value of alpha equals to 0, or positive solution f1 sigma square. Then we solve equation 3 for sigma square for given alpha, we can get sigma squared to be a solution which is referred to f2, a function of absolute value alpha and delta. So the f1 and f2 will look like this, which I should plot the figure for delta equals to 3.5. Now, the fixed point should be either the intersection of f2 and f1, or f2 and the y-axis, which is indicated by the 2 black points over there. Now, since we have multiple fixed points, a question will be which one should we converge to, and which one will we converge to? To show this, first I want to point out 2 important facts is that the movement from alpha t to alpha t plus 1, in most cases, will move towards the fixed point f1. And similarly, for a sigma t squared, the movements will, in most cases, will move towards the fixed point f2. So in this talk, let's simplify everything. Let's just assume in all cases, all these statements are true. Then, as the approximation I given before, we can see that the only correct fixed point is 1, 0. Now, for large enough delta, let's see this figure again for delta equals to 3.5. Now, let's suppose we initialize the P1 over here. Then, in the direction of alpha, we should move towards the curve F1 like this. And then, in the direction of sigma squared, we should move toward the curve F2 like this. So, for the next iteration, P2, we will move P1 to P2 like this. And similarly, we'll move T2 to the next iteration, P3 like this, and so on and so forth. And eventually, we can converge to the correct fixed point. Now, the convergence for the initialization over the other area can be more complicated. If you're interested in this kind of technique, you can check our paper for more details. Now, the thing is, if we make the delta to become smaller, which makes the problem becomes much harder, then the curve of F2 will become higher and higher, and eventually it will go above F1. Looks like this. So this is a figure for delta equals to 2.2. Now, as you can see, there's an intersection between the 2 curves, which introduce an additional fixed point, which is indicated by the 3rd black points. Now, if we initialize similar place around between these 2 curves, then based on the same update rules, we will eventually converge to the round fixed point, which is on the y-axis. So to conclude, the convergence, the transition happens exactly when the F2 is entirely below the curve F1 to partially above the F1. So that critical value for delta is equals to 64 over pi squared minus 4. So to conclude, our convergence results for the state evolution is the following. In the noisy setting, if delta is bigger than the critical value, which is about 2.48, then we have global convergence if the initial alpha 0 is bigger than 1, and the sigma 0 squared is smaller than 1. Now, if delta is only bigger than 2, we can have local convergence around 1, 0. That is, if we initialize within the purple curve, then we're able to converge to 1, 0. Otherwise, we cannot. And that region is also referred as the Bayesian attraction for 1, 0. I have to point out that this purple curve is heuristic drawing over there. And then if delta is less than 2, then, well, there's no correct convergence unless you initialize over there. Now, this basically answered the question for the first question. That is, the constant C will be exactly equal to the critical value over there, which is delta amp. Now, I'll begin to answer the question 2, which I refer to the noise sensitivity results. That is, in a high SNR regime, we can characterize exactly how much the asymptotic MSE can be amplified by the variance of the noise. And finally, I want to answer the final question, what is the impact of the initialization scheme? Well, as remember, there's a gap between the global convergence and the local convergence, which is about 0.48. Now, the question is, can spectral initialization can close that gap? Well, let's look at this figure. On the left-hand side, I plot the figure for delta equals to 2.4, and the right figure is for delta equals to 2.41. And the area defined on the upper left side over the red line is all the possible initialization can be given by the spectral method. And the region bounded by the blue curve is the attraction Bayesian for our AMPA algorithm. So as you can see, only starting at about 2.41, there's a chance that spatial initialization can give an initialization that can converge to the 1, 0, correct fixed point. So in that sense, the spatial initialization can only improve the threshold by only about 0.07, which is very, very small. So that means spatial initialization cannot help our AMPA algorithm, besides providing an estimate that is not orthogonal to the true signal. So finally, I want to have some comparison with other algorithms. That is, on the y-axis, we have successful rate, which is, we consider MSE is less than 10 to the minus 10 is a success over 100 trials. And then the algorithm we have compared with are the following. So we have AMPA over here, and incremental reshape vertical flow, and the Gershberg-Sexton algorithm, truncated amplitude flow, reweighted amplitude flow, truncated vertical flow, and here is the Bayesian gap. So the left-hand side is a figure for the complex value case, and the right-hand side is the real value one. And algorithm can be considered as better if it can have a higher successor rate for a fixed delta, or it can success for smaller delta because that means you have smaller sample size. So as you can see in both figures, our AMPA algorithm, which is the record over here and record over here, achieved the best in the complex value case and second best in the real value one. But I have to point out that the best algorithm in the real value case, which is the Bayesian gap, require additional knowledge about the true distribution of the true signal x0, or x star. So which is not required by all other algorithms. So finally, to conclude, I have raised these 3 questions. And can we specify the constant C for algorithm and compare the performance? Well, for our AMPA algorithm and under this asymptotic setting, and it works as long as the sample size is bigger than 64 over pi squared minus 4 times the dimension. And can we characterize the performance for the algorithm? Yes. In the high SNR, you can check our node sensitivity results. And finally, the impact of the initialization scheme, well, it cannot help besides providing an estimate that is not orthogonal to the true signal. So if you want more details, you can come to our poster, which is number 212 tonight. Thank you.
So we have some time for questions. Please use the microphone if you want to ask.
Can you elaborate on what you mean by the high SNR settings?
What? Can you repeat the question? Sorry.
What do you mean by high SNR? What is your cutoff?
So we didn't really cut off the high SNR here because it's a limit taking the sigma w to going to 0. That means it has high SNR. So basically, we approximate the first order about sigma w over here. So as long as sigma w is sufficiently small, then the first order constant is given by our results. Yeah. Thank you.
Let's finish for one time. So we like still like 2 minutes. So we still have 2 minutes to start. I don't care. Okay. It's like wait. We just wait like maybe 1 or 2 minutes before we start. Okay, so the next talk is given by Lucas. It will be about dissecting Adam algorithm.
Okay, thanks. This is joint work with my advisor Philip Hennig, and despite the somewhat violent title, we just want to understand the mechanisms underlying the Adam optimizer, and Adam won't be harmed in any way. So Adam is a very popular method for training neural networks, and training a neural net is an optimization problem of this form here, which I think everybody is familiar with. So we have a big sum over our training set, and for some choice of the parameters theta and some data point xk, L of theta and xk gives us a scalar loss value. Now, we would like to do gradient-based optimization on that objective, and the gradient, of course, inherits the sum structure, which makes it inefficient to compute in every step of our iterative optimizer, so we usually resort to stochastic gradients, meaning that we subsample a mini batch of data and compute the mean gradient only over this mini batch. Now that gives us an unbiased estimate, but it's imprecise, of course, and how noisy it is can be quantified by the element-wise variances of stochastic gradients, and we give this the name sigma squared I here. Okay, so the optimization methods that we commonly use in deep learning are very simple. Basically, we have SGD and its momentum variance, and then there's this family that many call adaptive methods, and that's AdaGrad, ARM-SPROP, AdaDelta, and maybe the most popular one being Adam, which we want to take a closer look at here. Okay, before I dive in, I want to clarify some notation. We use the usual shorthands like nabla L sub t or G sub t if we have a sequence theta t. And if we want to refer to the ith component of such a vector, we use double indices like this. And the next thing is crucial throughout the talk. If we use divisions or squares or square roots on vectors, that's to be understood element-wise. But we denote the element-wise multiplication explicitly to avoid any confusion. Okay, then let's get started on Adam. Adam maintains moving averages of stochastic gradients from past iterations, that's MT, and likewise for the element-wise square, that's VT. And then the update is essentially given by MT divided by the square root of VT. Now, as some of you will have noticed, I'm skipping over some details here, but that's the basic idea. And we start out from the simple observation that we can rewrite this update in the following way. By first separating the magnitude and the sign of MT, then pulling the magnitude into the denominator and under the square root, and then adding and subtracting 1 in the square root. Okay, we get this expression, which I have just copied over to the next slide. So the Adam update direction is given by the sign of MT, element-wise times this expression here. What is this object? Now, the name Adam stands for adaptive moments, and that's because the authors assume that MT approximates the first moment of the most recent stochastic gradient, and VT its element-wise second moment. And if we adopt this view, then the ith component of VT minus MT squared, which shows up here, is actually an estimate of the aforementioned variance of the stochastic gradient. Okay, a second observation is that the magnitude of MTI only appears in this ratio in the whole update equation. And under the same moment assumption, this might be viewed as an approximation of the variance of GTI divided by the square of its mean. So this is a relative variance, or if you like that better, a noise to signal ratio. And we give it the name eta squared. Okay, and from this decomposition, we conclude that Adam combines two aspects. The first one is taking the sign here, and that basically equalizes the update magnitudes across all coordinate directions, right? And then the second aspect on top of that is what we call variance adaptation, and that by which we mean that we apply element-wise factors to the update magnitudes, which are determined by and account for this noise-to-signal ratio. And in particular, we see that the ith coordinate is scaled with this expression, and this decreases as the relative variance grows. So the noisier some coordinate direction, the smaller or the more cautious our update step in that direction. And these factors also have the property that they have a maximum of 1 when eta equals 0, so when we have perfect gradient information, and then they go towards 0 when eta becomes very large. Okay, after this lengthy introduction, basically, I will tell you the purpose of this work. We wanted to disentangle these two aspects that I've just identified and try to understand them in isolation. And one means to do that is to consider all 4 possible recombinations of these two components. So Adam, as I just said, combines the both. SGD has neither of them. But then we can only take the sign, and this gives us stochastic sign descent, or sign SGD, or we abbreviate it SSD here. On the other hand, we can just apply this concept of variance adaptation directly on the stochastic gradients, which gives us a new method, which we call stochastic variance adapted gradient, or SVAG. And I will derive this method in a minute. Okay, I just promised you that I will analyze both these aspects, but I have to tell you that I will basically skip the first one, the sign aspect. One reason is time, and the other one is that there's concurrent work here at ICML, that's this paper down here, which does a much more comprehensive job of this analysis. But this slide is basically the 1-minute overview of what you can find on this sign aspect in our paper. And we asked basically the simple question, when can it be beneficial to use the sign of a stochastic gradient instead of the stochastic gradient itself? That is, we compare SGD to SSD. And we do so only on a very simple model problem, which is basically a noisy quadratic objective function with some Hessian matrix Q and some scalar noise level nu. And we look at this quantity here, which for some generic update direction C, basically tells us by how much we can expect the loss to decrease from a single update step in that direction. That evaluates to this expression here, and then we just compute this for both SGD and the sign descent method, and then we play around with properties of Q, the Hessian matrix, and nu, the noise level, and see how they affect this improvement. So for details, I will have to refer you to the paper and also to the concurrent work. Okay. So we move on to the second aspect, the variance adaptation, by which we mean these element-wise factors that account for the signal-to-noise ratio. Now, we have seen this at play in our decomposition of the Adam optimizer, but now we want to motivate this concept from scratch, so to say, and in the general case of any update direction P or its element-wise sign. So assume we want to update in this direction or its sign, but we only have access to an unbiased estimate P hat of P. Now we allow for such element-wise factors gamma, and the question is, what is the optimal choice for gamma? And one way to define optimal here would be to say that we want the L2 distance between our update, gamma times P hat, and the ideal desired P to be as small as possible in expectation over P hat. And this little lemma here basically says that for the non-sign case, this is solved by gamma I equals 1 divided by 1 plus eta I, which looks familiar. And in the sign case, the optimal choice is gamma I equals 2 rho I minus 1. And rho I is the success probability of our sign estimate. So if we take the sign of P hat, what's the probability that we get the correct sign for P in the ith component? Okay, now the big question is Adam consistent with this notion of variance adaptation? And the answer is kind of. So Adam uses these factors here, and the lemma just told us that the optimal variance adaptation factors are 2 rho I minus 1. But if we now assume G to be Gaussian distributed, centered around the true gradient, then we can compute rho I actually in closed form, and 2 rho I minus 1 in fact evaluates to this expression here. And if we plot the Adam factors and these optimal factors, we see that they are in fact pretty close to each other. So in that somewhat limited sense, we have identified the familiar Adam method as variance adapted stochastic sign descent. But we now have this broader concept of variance adaptation, and it would be a shame if we wouldn't apply it to different update directions. And the obvious candidate is the stochastic gradient itself. Now, we should use these factors for that case, and this gives us a new method, which we just give the name stochastic variance adapted gradient. And in this non-sign case, we can now nicely visualize this adaptation. So in this sketch, you see some 2D stochastic gradients in light blue scattered around the true gradient in dark blue. And the situation here is such that the relative variance is much higher in the theta 2 direction than in theta 1. Now, if we apply this variance adaptation scheme, we scale theta 2 back more drastically compared to theta 1. So we get these light red arrows. Now, their mean in dark red is biased away from the true gradient, but on average, the light red stochastic variance adapted gradients are closer to the true gradient in L2 distance. And that was exactly the motivation we started out with. Okay, an interesting side note is that if we had an oracle that we could query for the exact relative variances, and we would apply this adaptation, then this would guarantee convergence at the usual sublinear rate, but without having to decrease the global step size, which you have to do for SGD, because this variance adaptation has a step size decrease built in at exactly the right pace, so to say. But that's, of course, an idealized situation where we know the variances, the relative variances exactly. In practice, we have to estimate them, and I don't have really time to go through the details of our practical implementation, but the basic idea is that it's just similar to Adam. We compute the same moving averages. We use the same variance estimate that Adam is using implicitly, and then we just compute these new gamma factors and update like this. Now, I have grayed out some factors, as you can see here, because I couldn't discuss them in this talk, but these are minor scalar factors, and you can read up the details of this in the paper. Okay, so that's it for variance adaptation and for the SVHE. Now I want to talk about what's basically a side observation in this work, and it relates to the effect of the optimizer on the generalization performance. There was a paper at NIPS last year, which was called The Marginal Value of Adaptive Gradient Methods in Machine Learning. Sorry. And there the authors argued that adaptive methods have adverse effects on generalization. Now, they mostly substantiate this claim empirically, but they also put forward a theoretical argument based on a binary least squares classification problem. That's an objective function of this form, but the details of this are irrelevant for our purposes. What's important is that SGD on this problem class is guaranteed to converge to the max margin solution, which we expect to have favorable generalization properties. On the other hand, for some instances of this problem class, the adaptive methods, Adam, RMS-probe, etc., converge to solutions that generalize arbitrarily bad. Now, the authors construct such problem instances using this lemma down here, which basically says if the problem admits a solution of this form here, then these adaptive methods would converge to such a solution. Okay, so what we point out in our paper is that this statement very easily extends to the sign descent method. That's this lemma here. And if you look at the statement of the lemma and also its proof, then it's pretty obvious that this property is actually driven by the sign aspect. And on the other hand, this statement does not extend to SVHE, which is an adaptive method, but not a sign-based method. Together, this kind of suggests that the sign aspect of the two impedes generalization rather than the element-wise adaptivity as such, as this title suggests. Okay, finally I want to show some experimental results, and I've brought up this diagram again because these are the 4 methods that we compare experimentally. I want to quickly point out that they are all used in their momentum variant, which I didn't discuss at all in this talk, but we discuss in detail in the paper. Okay, we have 4 test problems. That's 2 vanilla CNNs on fashion MNIST in Cypher 10, a wide ResNet on Cypher 100, and an LSTM for language modeling. Okay, these are the results. The 4 columns are the 4 test problems, and we show training loss and test accuracy over the number of steps for all 4 methods. And I want to highlight 4 observations from these experiments. The first one is that of the 2 components that we argue are combined in Adam, the sign aspect is by far the dominant one. So these curves here distinctly cluster into sign-based methods, Adam and sign descent in orange and green, and non-sign-based methods, that's SGD and SVHE in blue and red. And the difference between sign-based and non-sign-based is much larger than between variance-adapted and not variance-adapted. Okay, second observation is that the usefulness of the sign is problem-dependent. That's pretty obvious. It's much better here. The sign-based methods are much better here, but they are, for example, worse here. And the theoretical part that I basically skipped has some ideas what might be the reasons for this. Okay, the third observation is that variance adaptation helps. In all experiments, Adam is as good as or better than sign descent, and SVHE is as good as or better than SGD. And finally, if you look at experiment 3, then this corroborates the suspicion about the generalization effects. So both sign-based methods, which have remarkably similar performance, are better in training loss than SGD, but worse in test accuracy. And SVHE, on the other hand, in red, which is an adaptive method but not a sign-based method, doesn't have these effects and indeed outperforms SGD slightly. Okay, let me conclude with a summary. We have argued that Adam combines these 2 aspects, taking the sign and variance adaptation. Taking the sign, we have observed that the usefulness is problem-dependent, and we also point out some underlying reasons for that. And we have also observed these adverse effects on generalization, which at least gives some indication that it might relate to the sign aspect. And that's probably an interesting point to follow up on. And then we have the variance adaptation. The basic idea is to manipulate the element-wise update magnitudes to account for the signal-to-noise ratio. We have shown that this is a general concept, not restricted to Adam. And in particular, we have proposed SVHE, which is a variance-adapted variant of SGD. And you can find a TensorFlow implementation of this method on GitHub. It's a direct replacement for the built-in TensorFlow optimizers, so please try it out and let us know how it works. Okay, our poster is number 16 tonight. Here are some ways to get in touch with us, and thanks for your attention, and I'm looking forward to questions.
So we have like 2 minutes for questions, so please use the microphone to ask questions. We have a question. How did you tune the parameters for the SGD momentum?
You mean for these experiments?
Yes.
So basically, we try to tune all methods, all hyperparameters of all methods with the same effort, let's say. So the momentum parameters are set to their usual standards, let's say, and then we tune the learning rate. Yeah.
How does this relate to the stochastic variance-reduced algorithms?
So with our name, we have kind of suggested a certain relation, maybe, but I think they are quite orthogonal because the variance-reduced methods try to build a lower variance gradient estimate, and this whole concept of variance adaptation just takes a gradient estimate as given and then tries to mitigate the effects of the remaining variants. So it might, in fact, be that we could combine the two. Yeah.
So it's thanks to the speaker. Okay, so the next speaker is Chris, and he will be speaking about the robust phase retrieval.
Cool. So this talk is about applying deep convolutional neural networks to develop noise-robust phase retrieval algorithms. So to set some context, we're interested in the following problem, where we have a vectorized signal we'd like to reconstruct, and we're given measurements y of the form y is equal to the absolute value of a measurement matrix A times x plus noise. This problem shows up in numerous applications, including astronomy, microscopy, crystallography, and more. And we're interested in a special case of phase retrieval where A is a DFT matrix and the signal X is real and non-negative. And we are motivated by two problems in particular: imaging through scattering media, things like fog and tissue, and imaging around corners. And in particular, we are interested in the following problem. You have a coherent illumination source, like an LED light, that illuminates the target, in this case a green car, and this scatters light that reflects light that goes into a scattering media like fog, and you image the result. And note that this looks nothing like the original car. The fog's too dense to see through it. A related problem is imaging around corners, where you have a camera and a laser co-located in such a way that they can't see the target, but you can bounce laser light off a wall onto the car, back to the wall, and then image that on the camera. In both these applications, essentially linear algebra lets you estimate the autocorrelation function of the target, that is x star x, and then you can use the relation that the Fourier transform of the autocorrelation is equal to the magnitude squared of the Fourier coefficients. From there, you can use phase retrieval to reconstruct the signal. Now, in both these applications, you can imagine that the vast majority of the photons that you send into the signal, either using the street lamp or the laser, aren't going to make it back to the camera. And so you're left with a large amount of shot noise, which we're going to model slightly inaccurately as Poisson noise on the Fourier coefficients squared. Now, this poses a major issue, as the majority of phase retrieval algorithms weren't really designed to work with noise. This is especially true of classical techniques like Gershberg-Saxon HIO that rely on alternating projection. And although some of the optimization-based techniques, which were talked about earlier, can handle noise by imposing priors like smoothness or sparsity, they're generally designed for more theoretical problems where you have IID Gaussian measurements or coded diffraction patterns. A notable exception is plug-and-play ADMM that was recently extended to phase retrieval. This method imposes priors using image denoisers. It can handle Fourier measurements. It's fairly robust to noise, but because it's using image denoisers like BM3D, it can be computationally expensive, and at present there isn't a public implementation. So in this work, we're going to apply convolutional neural networks to the phase retrieval problem to develop fast and noise-robust algorithms that can handle Fourier measurements. So the typical approach to handle phase retrieval and really any imaging inverse problem with neural networks is as follows. You have a series of training points, x1 through xn, which lie in the signal class that you're interested in. For instance, the class of all natural images. And you then either generate or capture a corresponding set of measurements, y1 to yn, where x1 maps to y1, x2 maps to y2, et cetera. And then you would train a neural network to simply learn the mapping back from the measurement space to the signal space using gradient descent or some other technique. Now this works, and it has been done, but the major issue with this approach is that essentially you've trained your network for a particular measurement operator. And if things change, your training, you have to completely retrain. So for instance, if you apply a bandpass filter on your measurements, you now you have a mapping from the dash set to the signal space, and you're now interested in a mapping from a completely different set. So in this work, we advocate doing something different. we instead suggest using a CNN as part of a larger algorithm that's able to take advantage of the known measurement operator. In particular, we start off with an iterative algorithm that imposes priors using image denoisers, where you can think of an ideal image denoiser as a bit like a projection onto the set of natural images or onto the manifold. You then train a neural network to be an image denoiser, to denoise natural images, and simply plug that CNN into your original algorithm. So the simplest example of such an algorithm works as follows. It consists of 3 steps. First, given your current estimate of the signal, you compute your predicted measurements. That is, you move into the measurement space. You compute your error with what you actually observed, and use that to take a gradient step back in the signal space. And then you impose a prior using your CNN. And you can repeat this process over and over again in the hopes of arriving at a fixed point. Now, the nice thing about this approach is that because the yellow and green steps incorporate the measurement operator, if it changes, the algorithm automatically adapts. You don't need to do any sort of retraining. So in this work, we trained the state-of-the-art DN-CNN image denoiser, which consists of 20 convolutional layers with batch normalizations and ReLUs stacked in between. And we trained it using 300,000 patches, which takes about 3 hours on a Titan X. We then put it into the following optimization framework, which consists of 2 terms. First, an L2 to amplitude loss function on the left, which penalizes differences between your observations and your predicted observations, absolute value of fx. And then a second term on the right, which comes from a paper called regularization by denoising. And parsing this a little bit, note that it's the inner product between the current estimate of your signal, x, and your residual. That is the difference between x and its denoised self. This serves 2 purposes. X minus dx will be small if the denoiser doesn't change x. The denoiser won't change natural images, but it'll change noisy images quite a ton. Simultaneously, it enforces the residual x minus dx not to contain structure. If it removes structure from the signal, the resulting residual is going to be correlated with x. Now, once you have this expression, you can derive an analytic subgradient for the data fidelity term, and a proximal mapping for the regularization term, which opens you up to using a variety of optimization frameworks, including FASTA, which is what we used here. Note that the left term is highly non-convex, so you need to initialize it. We use the HIO algorithm. And I should point out that the majority of the initializers you might have heard, the spectral initializers you might have heard of previously, don't work well with these Fourier measurements. So shown here are some reconstruction results comparing the baseline HIO algorithm with the neural network-based approach. It takes about twice as long, but produces a much better reconstruction. This compares favorably to the plug-and-play ADMM algorithm as well. It produces fewer artifacts and runs about twice as fast. So to summarize, phase retrieval algorithms show up in numerous applications. And Fourier phase retrieval is a particularly interesting class that can enable new applications like imaging through scattering media. Unfortunately, in these applications, you're subject to a large amount of noise. In this work, we used neural networks to make more robust phase retrieval algorithms. If you'd like to learn more about this work, talk to me at the poster session. I'm at 164, and our code is available online. Thank you.
So we have some time for questions.
So it wasn't clear to me where the computational gains come from instead of making the algorithm faster. In a sense, I understood that the neural network is used as a prior, so if you didn't use it as a prior and just solve the inverse problem, it would be faster, I would imagine.
I'm not sure I understand. Can you?
Maybe if you could just tell us again where why the algorithm is faster.
Okay. So I don't want to stress computation times because it's essentially implementation differences. But compared to plug-and-play ADMM, the image denoiser we use is much faster than the image denoisers used in plug-and-play ADMM. If you were to use the denoiser inside plug-and-play ADMM, computation times become comparable. Essentially, we made 2 changes, red and the neural network. red is incrementally faster. The neural network gives you the performance gain.
And the other question I had is why decouple the problems? Why can one learn the network and solve the inverse problem together?
So I think the motivation for the decoupling is that in a variety of in these applications, you're going to be changing your experimental setup all the time, and you don't want to have to recapture and retrain. There's nothing stopping you from learning just a mapping from the measurements to the signal. This lets you adapt to new measurement scenarios.
So I think that we don't have more time, so we can take it offline
Okay.
for the poster session.
That's good. Thank you.
Okay, so the next talk will be done by Yang Song about accelerating natural gradient.
Hello everyone, my name is Yang Song. My presentation is on accelerating natural gradient with higher order invariance. This is a joint work with my colleague Jiaming Song and my advisor Stefano Amon at Stanford University. In supervised learning, we aim to optimize probabilistic models that can jointly capture the distribution of input X and label Y. A model can have several different parameterizations. For example, let's consider a linear regression problem with Gaussian noise. We can directly parameterize the weight by a parameter theta. We can also add a rescaling constant, and so that the parameter is parameterized by 2 mu. Obviously, those two kinds of parameterizations, they result in the same model family. We say an optimization algorithm, it tries to take a parameter under some specific parameterization and gives another parameter. For example, we can use gradient descent to maximize the conditional log likelihood of the linear regression model. We say an optimization algorithm is invariant if given a specific probabilistic model, no matter what parameterization is used, the next model is the same. Unfortunately, the gradient descent method doesn't hold this property. Let's return to our linear regression model example. Since theta t is exactly twice the number of mu t, so the gradient with respect to theta t will be half the gradient with respect to mu t. And since when we update mu t, we use the same learning rate, the step size will be larger compared to the step size of theta. There has also been some efforts of improving the invariance of optimizers. For example, ADA grade, it uses a scaling factor so that the optimizer is invariant to scalings of parameters. And also Newton's method, it uses a preconditioning matrix so that the parameter, so that the optimizer is invariant to fine transformations of parameters. Probably the algorithm that currently has the best invariance property is natural gradient method. And we show its update formula as follows. Here, theta is the parameter, and h times lambda is the learning rate. L is the loss function, and G mu nu denotes the coefficients of the inverse Fisher information matrix. Usually in practice, we set the learning rate to be a scalar close to 1. We show that this natural gradient update can be viewed as approximately solving the following natural gradient ODE with forward Euler method. In the paper, we show that the solution of this natural gradient ODE is exactly invariant to any differentiable parameterizations. Unfortunately, since we use the forward Euler method to solve this ODE, the finite step size used in the solver will cause the loss of invariance. To put it more clearly, let's see an example of using the natural gradient update to fit a univariant gamma distribution. So a gamma distribution has two parameters, alpha and beta. We can try to transform them to
create different parameterizations. In the following figure, we show how log likelihood decreases with respect to the number of iterations. We expect that as there are more iterations, negative log likelihood, it should decrease. The title of each figure shows how we transform those parameters to create new parameterizations. The solid line is a shape, is a curve of the natural gradient update, while the dashed line is a curve of the exact solution to the natural gradient ODE. From the figures, we can see that the shape of those dashed lines, they are the same for different parameterizations, but the shape of the solid lines, they are different for different transformations. So this finite step size causes a loss of invariance. Since the natural gradient ODE is invariant, we propose to use more accurate solvers to solve the natural gradient ODE so that we can preserve the invariance better. Here we choose a midpoint integrator. It first computes the natural gradient direction, which is the same as the forward Euler method, but only use half the step size to do the update, so that it gets an intermediate parameter theta k plus 1/2. And then it computes the gradient and this intermediate parameter and uses the gradient to do the final update. So midpoint integrator, it converts to the solution of natural gradient ODE in second order compared to the first order solution is more invariant. Although midpoint integrator, it can be more invariant, it's still not exactly invariant because it is still using a finite step size. People in the numerical analysis literature, they actually come up with a method called Riemannian Euler method, which is exactly invariant, even though the step size is finite. So in the following update rule, EXP denotes the exponential map. Intuitively, we can understand the exponential map as, it follows a geodesic line and starting from a given point and runs in the direction of a given vector for a unit time. So compared to forward Euler method, which updates the parameter in the parameter space following a straight line, the Riemannian Euler method updates its parameter following a geodesic on the manifold. However, the exponential map is usually intractable to compute. So we propose to leverage the geodesic equation to approximate the exponential in second order. From this updated rule, we can see that our updated rule with geodesic correction is basically a combination of natural gradient update and a geodesic correction term. Here, the first two terms is exactly the natural gradient update, and the second term is something we add to it to make it more invariant. The computational complexity in computing natural gradient update is mainly computing the inverse Fisher information matrix. However, if we compute the geodesic term, it means we need to compute the inverse Fisher information matrix twice, which is computationally expensive. In the paper, we show that there exists a faster geodesic correction method which does not need to compute the inverse Fisher information matrix and hence has similar computational complexity to natural gradient method. In the paper, we also prove a theorem to show that geodesic corrections, including the faster version, they converge to the solution of a Riemannian Euler method in second order, while we can view the vanilla natural gradient updates as converging to the exact solution of Riemannian Euler method in first order. Okay, so let's test our algorithms again on the toy example fitting gamma distribution. Here we add the exact solution of Riemannian Euler method, which is in dashed blue. Similar to the natural gradient ODE solution, it is exactly invariant for different parameterizations. Our proposed midpoint integrator and geodesic corrections, they are also closer to the invariant curve and converge faster. We also conduct experiments on training deep neural networks. In the image, we show training deep autoencoder on the MNIST dataset. So the y-axis is training error, and we expect it decreases with respect to time and the number of iterations. There are two axes in the figure. The top axis is time. The bottom axis is number of iterations. And for each algorithm, we show both a solid curve and a dashed curve, where the solid curve represents performance with respect to number of iterations, and the dashed curve represents performance with respect of time. So from the figure, we can see that our proposed faster geodesic correction, it actually decreases faster than the natural gradient method in terms of time. And our methods, they all decrease faster in terms of our iterations. And finally, we show some results on reinforcement learning using policy gradient. So in this figure, the x-axis is the time steps, which is proportional to number to sample complexity. The y-axis is x per episode reward, which we hope to maximize as fast as possible. So this red line represents ANCTR, which is an algorithm based on natural policy gradient. And it's clear that our methods it converts faster with less sample complexity. And finally, to conclude, our take-home message, first, natural gradient update is not invariant when the step size is finite. And second, more sophisticated numerical methods for ODE solving can actually improve invariance and with a similar computational cost to natural gradient. Third, invariance can improve performance empirically in supervised, unsupervised, and some reinforcement applications. Okay, that's it. Welcome to our poster session tonight. The poster number is 70.
So we are out of time, so next speaker will be from the session on non convex optimization for. So the next talk will be given by Sebastian. It will be about stochastic Wasserstein barycenters.
All right. Hi, everyone. My name is Sebastian, and I will be presenting joint work with a postdoc, Ed, in our group, and my advisor, Justin Solomon, on stochastic Wasserstein barycenters. So I know that's a bit of a mouthful, but hopefully throughout this talk, you'll come to understand what those words mean better. Okay, so what's the motivation behind this? Well, in machine learning, as you all know probably much better than I do, you have a lot of data. And that data typically comes from multiple sources, and sometimes you want to summarize it. So for instance, let's say you have weather data that comes from multiple weather stations. You want to know what the weather is like at a specific point. Or you have a sensor network, which is monitoring the same random variable, and you want to summarize the impact of each individual node. For a more ML-themed application, consider running MCMC on subsets. You have your subset posteriors. What's the posterior of your true distribution? Right, in all of these cases, what you want to do is you want to average your distributions in some way such that the result makes sense. And the way we're going to be solving this problem is through the lens of optimal transport. Now, optimal transport, you can think of it as a geometry for probability measures. And the intuition behind it is remarkably simple. It's essentially you're moving piles of sand. Let's say your sand is currently the blue distribution, and you want to put it all into the sandpit of the orange distribution. How do you do that whilst using as little effort as possible? You're a lazy man. Okay, so the way to quantify the amount of effort necessary is through the Wasserstein distance. Now, the two Wasserstein distance between two measures, mu1 and mu2, is this rather scary-looking integral over the set of all couplings between mu1 and mu2. The intuition behind this is that the couplings tell you where to shovel the sand from and towards. All right, so now returning to our original problem of finding averages or barycenters in probability space. So it's often the case that we want to average distributions. Let's say we have these example digits from MNIST. We're curious, what's the average 6 going to look like? Well, there's one obvious way to do the average, which is in Euclidean space. The problem is that Euclidean average doesn't contain geometric information. So if your 6s are just slightly shifted away from the center, then what you get is essentially garbage. But what you want is something that still looks like a 6. So what can be used to solve this problem is what's known as the Wasserstein barycenter, which is just the barycenter with respect to the Wasserstein distance. The way to think about this is that all that equation is saying, or the analog of that equation is just the, in Euclidean space, is just the standard mean. Like if you replace W2 squared there with squared Euclidean distance, what you recover at the end is the standard Euclidean mean. So why would you want to do Wasserstein barycenters? Well, you probably got the memo at the first time I mentioned this. The Wasserstein barycenter makes sense in most cases. So for instance, if I have those 3 Gaussians up there, and I take the Euclidean average, that's not exactly what I expect the mean distribution to be. Whilst if I do the Wasserstein barycenter, what I obtain is a Gaussian with the same covariance as the initial ones, but centered at the mean of the means. So we're obviously not the first to have thought about doing Wasserstein barycenters. The notion of the Wasserstein barycenter was first introduced in 2011 in a seminal paper by Aguet and Carlier. On the more computational side, we have the entropically regularized schemes of Couturier and Doucet, which show that the Wasserstein barycenter can be computed efficiently for large-scale machine learning problems. This method was extended to work on non-Euclidean domains by Solomon et al., and recent work has focused primarily on making the Wasserstein barycenter computation parallel and distributed. So what's different about our method? Well, first, it's non-regularized, and it works with arbitrary continuous measures. And how we're going to do this is we're first going to make the assumption that the barycenter can be approximated by a discrete uniform measure. So the barycenter is just a sum of deltas, a weighted sum of deltas. And all we're going to be optimizing over is the positions of the support points. So all we optimize over is the xi's. And the way we're going to be doing this is using the Kantorovich duality and an alternating optimization scheme. And as I mentioned, we only assume we have sample access to our input distributions, and they can be absolutely continuous with respect to Lebesgue. So to simplify, the barycenter problem is additive. So from now on, I'm only going to be considering the barycenter of a single continuous distribution. And in the end, I'll explain how you go from that to solving the barycenter problem. And what an alternative way of formulating this is, what is the best discrete uniform approximation for a given measure? So for instance, here is what I would say the best discrete uniform approximation for this mixture of Gaussians would be. All right, so I mentioned duality. The Wasserstein cost has an equivalent dual problem, which is given up there. You don't have to think too hard about the equation. There is a very simple supply-demand interpretation. So whilst the problem, the primal problem asked you to shovel sand from point A to point B, the dual problem is telling you, well, okay, I'm a merchant. I want to take my sand from point A, buy it from point A, and sell it in point B. What's the most profit I can make doing this under the constraint that it's never cheaper for someone at point B to buy it at point A and just ship it over? Okay, right. So when one measure is discrete, which is the case in our case, since we're assuming the barycenter is discrete and uniform, this simplifies a lot. And right now, the optimization over the function f reduces to an optimization over a vector in Rm. And the infimum in the previous slide can be pulled out to the integral. And in fact, You can specify it as a sum of integrals over Voronoi regions. Well, generalized Voronoi regions, so slightly weighted Voronoi regions. All right, so this is an optimization problem. We're going to compute gradients, naturally. The dual problem is concave in the weights. We can apply gradient descent, and the gradient in this case is very simple and very intuitive. All it wants is that each individual point, the cell of that point, assumes equal mass. It assumes mass 1 over m. So each individual point is responsible for the same amount of mass as every other point. The optimization with respect to the points, unfortunately, is non-convex. But taking the gradient yields a very simple fixed point iteration where the position of the current point xi, you update it to the position of the barycenter of the Voronoi cell you're in. This has some connections to the semi-discrete problem where you want to map a continuous distribution to a discrete one. And for a bit more intuition, let's take this very simple example. Let's say my continuous distribution is uniform over d square, and my discrete distribution is just uniform over x1 and x2. Right, and now let's say that the fi, in this case there's only one, the fi controls the position of the separating hyperplane between x1 and x2. So what I first want to do, using the gradient for the weights, what I first want to do is I want to adjust the position of the hyperplane such that both x1 and x2 are responsible for half of the mass of mu2. So I do that, and now the separating hyperplane is in the middle. And when I move the points, what I'm doing is I'm moving x1 from its current position to the barycenter of the cell. And the reason I'm doing these two steps one after the other is that both of them reduce transport cost. So the algorithm, this is only slightly simplified. The full algorithm in our paper is about twice the length of this. So we sample seed points, and we repeat until convergence. We first solve for the weights, and then we shift points via a fixed point iteration. To extend this to the barycenter, we simply sum the gradients, and we carry on computation as before. So a few results. There are some cases, not many, where we know what the true barycenter should be. This is one particularly simple case. Our input distributions are uniform over the interior of the unit cubes. Those are shown in blue. The true barycenter is a uniform distribution over a unit cube at the midpoint between the two distributions. And in red, I'm showing samples from our barycenter. That should be about 100 points. And they're all within the support of the true barycenter. One advantage of our method versus competing entropic regularized ones is that it preserves sharp features. So here, the input distributions are uniform distributions over the contours of the 20 ellipses shown there. The ellipses are randomly drawn. There is some theory saying that the true barycenter in this case should be the unit circle centered at the origin. And we do indeed recover that with 100 samples. The entropically regularized version, while it does look like a circle, is in fact non-zero almost everywhere, has non-zero mass almost everywhere. More results on sharp features. Here, the input distributions are uniform over the line segments. We don't know what the true barycenter in this case should be, but we do expect it to be a line, and we do recover something that looks like a line. There are some nice applications of this for the one distribution case. So if I have a single distribution and I'm asking what is the best endpoint approximation to it, if I do this for images, for grayscale images, what I get is a blue noise approximation. So essentially like a half-toning algorithm, but without being able to vary the size of the points. I can also do this for a mixture of Gaussians, and I'm showing on the left uniform samples from that same mixture, and on the right samples drawn using our algorithm. And you can see that our algorithm much better approximates the contours of the of the distribution. So the takeaway message is that our algorithm can compute Wasserstein barycenters without regularization for arbitrary amounts of continuous distributions. It is easy to implement and highly parallelizable. Thank you, and come see our poster at number 69 for more hairy details.
So we have 5 minutes for questions.
So are there like guarantees for certain types of barycenter problems, or things like knowing the duality gap, or other things like the Hess?
You mean, so are you asking about guarantees in the sense that we know what the true barycenter should be, or are you asking about there?
Or I guess like how close your like value of the objective is to the true one?
Oh, okay. So we have a very, very weak convergence result. And theory seems to back us up that there is only a very weak notion of convergence in this case. That is, our notion of convergence is that there is a weakly convergent subsequence, because our method is essentially a fixed point iteration. What we can say for certain is that the transport cost will decrease at every iteration, at every step of every iteration.
Let me ask one more question, which is, do you have any lower bounds? Like, you can't compute these barycenters exactly, or you can't, like, is there lower bounds for that, or you can't approximate them or something like this?
I don't know, but I would be very curious to hear your thoughts on this offline if you want to come talk to us.
Hi.
Hi.
The problem of computing the barycenter of probability distribution has a long history in information geometry, and it can be solved using other metrics, such as the Fisher-Rao metric, for which you know that you can derive conditions under which the barycenter exists, is unique, and things like that. So I'm curious as to what are the advantages of using the Wasserstein distance versus using the Fisher-Rao metric, particularly given that it appears you wouldn't have results of convergence or uniqueness of the barycenter, or so on and so forth.
You do have results of uniqueness and existence, but indeed the convergence results reflect our approach, which essentially takes a successfully better approximation of the barycenter. If you could prove convergence of this approach let me put it this way. If you could prove that this converges at a specific rate, you have a proof that k-means also converges at a specific rate. So it's not quite so trivial, but our empirical results do look very, very good. As to whether you would use Wasserstein or Fisher-Rao, I guess that's application dependent.
Any other questions? If not, let's thanks to the speaker.
Thanks.
To mirror the displays.
I guess I just have to move it.
That's how it works. You will not see it.
Oh, that's bad.
You need to mirror the displays. You go to displays.
That's fine. I will figure it out, I guess.
Can go to the slide.
Yeah, this is the first slide.
So the next talk is given by Summit, and we speak about learning compact neural networks.
So
I'll be talking about my paper titled Learning Compact Neural Nets with Regularization. So let's start with some motivation. As you know, production deep learning models contain millions of parameters, and it is important to have parameter efficiency to make sure that basically the training process goes smoothly, or the eventual model we find has some nice properties such as generalization. So regularization heuristics is pretty useful to achieve that. So what do I mean by that? Let me give you some examples. One example is convolutional neural nets. It is essentially some efficient neural network architecture, right? And each filter is essentially being used multiple times throughout the image, right? Each receptive fields and each filter is interacting with each other throughout the image. Similarly, weight decay is essentially a L2 regularization heuristic. It prevents extreme weights and it helps with generalization. It's essentially some kind of ridge regression for neural nets. And quantization and pruning heuristics lead to compact models with either a few bits or few non-zeros, which is good for, let's say, mobile computing purposes. Overall, the point of this talk is proper regularization can improve generalization performance, storage cost, and computational efficiency. And our goal in this talk will be essentially providing some kind of theoretical insight for neural network regularization. Let's introduce our setup. We will be talking about a two-layer neural net model throughout this talk. And this model is parameterized by an activation function phi and some output weights v and input weight matrix w. And the input-output relation is essentially given by the picture. So what is specific about this talk? We'll be talking about learning such a neural network model over some constraint set C. The talk is essentially, our results are applicable to a general constraint set, but obviously this constraint set can be tailored towards specific application. In particular, if my application is pruning, then I want my constraint set to contain few non-zero weights. It will contain matrices W with few non-zero weights. If my application is convolutional neural nets, then it will contain matrices with repeated weights. And if my application is quantization, then my weight matrix will have either discrete or quantized entries. So to move into the theoretical part, what we will do is we will study a regression problem. We assume we have a data set of size n, and we will try to fit a least squares loss to this data set. And our optimization task will be minimizing those loss with the caveat that I want to do this minimization over some constraint set C. So let me describe our contributions before moving further towards theory. So I would say one-line contribution is within our framework, we show that regularization can achieve data and computational efficiency. Specifically, what we do in this work is we first quantify the benefit of regularization by introducing a covering dimension. And basically, what happens is that if this covering dimension or the covering number is smaller, then we will need less data for training. And secondly, we analyze, for the training purposes, we analyze the projected gradient descent algorithm, which is a slight modification of gradient descent, which also takes into account the regularization part. And what we show in this work is we show that projected gradient descent can achieve linear convergence around the global optimum, and it does this with near optimal sample complexity in terms of covering dimension. And a desirable aspect of our results is that our results are agnostic. We don't really care about what kind of constraint we are using. It can apply to convolutional constraints or sparsity and low-rank priors. So let's move forward. And the theoretical framework is essentially using tools from high-dimensional statistics, not surprisingly. And the first tool will be, as we discussed, the covering dimension of the constraint set. And in order to understand what is a covering dimension, from the previous slide, I'm essentially covering the set with some balls. But this covering dimension is essentially logarithm of the covering number with respect to L2 norm, with the caveat that basically I adjusted for the covering resolution epsilon. Basically, I wanted to have some kind of nice property for all epsilon uniformly. Okay. And then the second quantity we need is the set of feasible directions. And it is essentially a function of a set and a matrix W. And what happens is that it is the set of steps I can take from W that still keeps me inside the constraint set, C. Okay, this is the CW set. And it is highlighted by the red region. So with these two, we can quantify the impact of regularization as follows. First, we make an assumption in order to do this, that there is a W star, weight matrix W star, that governs the relationship between input and output. With this assumption, our critical quantity in this work reduces to the covering dimension around the ground truth W star, which is what we call CD CW star. So recall that CD is basically covering dimension of a set. So just to give some concrete examples to see what happens, I think this table is pretty useful. So what happens is that if there is no constraint, then I am dealing with a weight matrix of Kp dimension, K times P, and covering dimension is just K times P. If there is a convolutional constraint, which I will go into it later, it is SP. If there is a subspace constraint with, if it is a S-dimensional subspace, then the covering dimension will be S, basically. In summary, in all of these examples, the covering dimension corresponds to the degrees of freedom of the constraint set. So let's go towards our main result. So let's just first introduce the projected gradient descent algorithm. It is a very classical idea. Basically, what we do is we take a gradient step first, and then at each iteration we take a gradient step, and then we project our iterate to the constraint set. So obviously, this is a classical idea, and like it has been used in many contexts. And our main result is described as follows. It provides a linear convergence guarantee around the ground truth. So what happens is that we assume we have a data set of size n, and we assume that basically there is a ground truth matrix W star that governs the input-output relationship. And we assume activation function is smooth, set C is convex, and W star is inside the constraint set. And then we say that if the number of samples exceed the covering dimension, and if the initialization is fairly close means essentially we can go into it later, but if the initialization is close to the W star, then starting from that point, projected gradient descent linearly converges to the ground truth solution. So these are main theorem. There are a couple of other results in the paper, which we can discuss offline. But there are two remarks that I need to do, I need to state regarding this theorem. And both of them are essentially coming from previous and this year's ICML papers. The first remark is that it is really not possible to do much better than this result in terms of the convergence of gradient descent. The reason is that it has been shown that even without regularization, gradient descent can get stuck in local minima. This is like ICML paper of this year. And second result is that while this guarantee is local, it can be combined with other initialization schemes such as tensor methods or maybe some overparameterization tricks to achieve global convergence. Okay, so I will talk about two applications of our result. And the first application is somewhat funnily the one with no constraints. It is just plain gradient descent, just to compare with the existing literature. So there are a couple of works that considered this local convergence result. And compared to them, basically all of the existing works are kind of optimal in the input dimension size P, but our result is also optimal in the number of neurons, K. So that's like one nice property of our framework. We essentially achieve, if there's no constraint, there are Kp degrees of freedom, and we need Kp samples. It is nice, basically. And the second application would be modeling convolutional neural nets as fully connected networks subject to a subspace constraint. Basically, if you have a convolutional neural net, let's say 2 layers with S filters of size B, you have in total S times B degrees of freedom. And you can show that basically this is a S times B dimensional subspace on the constraint set. And then we have local convergence guarantee with SB samples without any structural assumption. And finally, I will talk briefly about numerical simulations. So I conducted some synthetic simulations with some sparsity constraint. The takeaway is that, at least for the synthetic simulations, I don't have time too much into large-scale simulations. At least for the synthetic, whether initialization is closed or random, regularization helps quite a bit. One surprising thing is random initialization helps, but it is worse than the closed initialization. Another thing is our result applies to convex regularizers. And indeed, surprisingly, L1 is much better than L0, especially for the random initialization. And this concludes my talk. Overall, basically, we provide some guarantees for neural network regularization. And the interesting directions would be global convergence with regularization, as well as deep network extensions.
So we have like 30 seconds for the question, if someone wants to ask.
There is something that I don't understand in your result, which is that in general, to get linear convergence, you would need to have an assumption like strong convexity or some weaker assumption, which can be like Polyakov-Yazevich type inequality. And here, if I understand well, if the constraint set is just Rn, you obtain a linear convergence rate. So can you explain how you can get a linear convergence rate without making assumptions, or where is hidden the assumption about the curvature of the function?
I see. So basically, the strong assumption that we are making is we are already initializing close to a W star. So that's the strong assumption we are making. And secondly, we are essentially using restricted strong convexity kind of ideas to achieve strong convexity around that point. So the strong assumption we are making is our initialization. And the result is statistical in the sense that basically the data is IID and Gaussian.
Okay, but you say you use some form of restricted strong convexity. If you just have a constraint set, how does that give restricted strong convexity?
I guess we have to take it offline.
Sure, thanks.
So the next talk will be about Riemannian stochastic recursive gradient algorithm. Does it work?
Hello, everyone. My name is Hiroki Kasai from the University of Electrocommunications in Japan. Today, I will talk about the Riemannian stochastic recursive gradient algorithm. This is a joint work with Hiroyuki Sato, Kyoto University in Japan, and Pandit Mishra, Microsoft in India. We consider the finite sum problems. So here, n is the number of samples, and it is assumed to be large. And W is the model parameter, and it is on a Riemannian manifold. So we have many applications, including PCA, matrix completion, and subspace tracking problems. So here, we consider the stochastic approach like Riemannian stochastic gradient descent, RSGD. So this approach seems to be not a good idea because we require retraction and vector transport operations every iteration. However, in a wide range of applications, such as higher order tensor completion problem, the cost of the Riemannian gradient is dominant. In such a case, this approach is scalable and really promising. So contributions, we propose a Riemannian stochastic recursive gradient algorithm, which is called RSRG. So our analysts deal with the both retraction convex and the non-convex functions. So we consider the computationally efficient retraction and vector transport operations instead of the exponential mapping and parallel translation. So this analysis is very, very challenging. So we get the convergence analysis for the both functions. And finally, the total complexity is obtained with respect to the reduction and vector transport parameters. So this is the first result as far as we know. So this is the algorithm. So RSRG algorithm updates the current iterate WT by moving along the reduction curve in the direction of the modified Riemannian modified stochastic gradient. So this is the typical approach in the Riemannian setting. The one different point is that we have a double loop structure as RSVRZ. So this slide focusing on the distinct feature of our RSRG. The point is that the calculation of the modified stochastic gradient Vt. So this Vt is calculated from the stochastic gradient at the current point Wt, and also we calculate from the stochastic gradient from at the previous iterate Wt minus 1, and also we use the modified stochastic gradient Vt minus 1. So they are transported from the previous point Wt minus 1 to Wt by vector transport. This is because that these belong to a different tangent space. The simple addition operation is not well defined on the Riemannian manifold, because manifold is not a vector space. So I want to ask to get your attention on the following 2 points. The one is that we use the stochastic gradient at the previous point Wt minus 1, and the second point is that this is the modified stochastic gradient, which is recursively updated. So comparing with RSVRZ algorithm uses the stochastic gradient and the full gradient at the outer loop edge point W tilde. This is the most biggest difference. So this RSRZ is a generalization of the Sala algorithm proposed in the Euclidean space into the Riemannian setting. So like Sala, RSVRZ has an accelerated variant, which is called RSRG plus. So this RSRG plus has a adaptive inner product, adaptive length of inner loop. So RSRG plus stops the inner loop when the norm of the modified stochastic gradient gets lower than the sum ratio of the initial value. So this is heavily dependent on the linear convergent property of the norm of the stochastic modified gradient in the retraction convex functions. So this is the one result of the norm of the modified stochastic gradient Vt. The red one is the RSVRZ, and the blue one is RSRG. So as you see, that the RSRG has a linear convergent of the norm of the modified stochastic gradient Vt. So let me summarize the advantages of the RSRG. So as I said, the RSRG transports the vectors from the previous point Wt minus 1. So this is the most important point, specialized in the Riemannian setting, because this advantages becomes much more clearer by comparing with RSVRG. So RSVRG transport the vectors between two distant iterates. Therefore, RSRG requires the existence of the inverse of retraction for vector transport. And also, the RSVRG needs to calculate the inverse of the retraction for every iteration. On the other hand, RSRG does not need to calculate the inverse of the retraction every iteration. So that's why RSRG is computationally efficient. Also, it allows us to apply RSRG to a wider range of the manifolds, including a Stifel manifold and the fixed rank manifold. So we have obtained the linear rate convergence rate for the retraction convex functions, and also we have a sublinear rate in a single outer loop for general convex functions. And finally, we have a linear rate in the gradient dominant functions. So we analyze the total complexities with respect to the parameters that directly connected with the retraction and parallel vector transport. So they include the theta, which is the deviation parameter between parallel translation and vector transport. The second one is rho L, is the ratio of the Lipschitz constants between the exponential mapping and the retraction. The nu is also the deviation parameter in the inner products between the inverse of the exponential mapping and retraction. So as expected, the worst case total complexity is getting worse when the retraction and the vector transport deviates from the corresponding exponential mapping and parallel translation. So we also provide the comparison with the RSVRZ for exponential mapping and parallel translation case. So let me show you the one example of the numerical evaluations on Riemannian centroid problem. So here we calculate as Riemannian centroid for the n symmetrical positive definite matrices, size of D times D. So here n is 10,000 and D is the dimension is the 30. So this figure shows the functional optimal gap. So as you see that the blue line is ours, RSRG. So RSRG is comparable to RSRG, SVRG, or RSRG plus is much better than other algorithms. So for more details, please find us at number 179. Thank you.
So we are out of time, so we will leave the questions for the poster session. Thank you. Okay, so the next talk will be about lowering Riemannian optimization and application in graph clustering.
Thank you very much. Yeah, so the title is a mouthful, low-rank Riemannian optimization on PSD stochastic matrices with applications to graph clustering. So this is work primarily of my student Ahmed Duk. Ahmed was hoping to be here, was waiting for his visa till the last minute. Did not happen. He sent me the slides earlier today. He sent me the slides, not the LaTeX files. It's 17 slides, but I hope to finish in 10 minutes. But had I had the LaTeX slides, I would have shortened it a bit. So this talk, it's kind of fortuitous because the previous talk was on Riemannian optimization, and this is too, and I'll kind of tell you what the context is. So we want to do low-rank optimization on the set of stochastic matrices. And the reason why we're interested in this is because we were interested in doing graph clustering. So there's recently been a slew of convex optimization methods to do graph clustering where you're given partial observations, say, of the noisy adjacency matrix or a similarity matrix of a graph, and you want to cluster the items in the graph, if you will. And one can give, provable guarantees. The convex method works quite well. The drawback is that it's computationally intensive and doesn't really scale. And so the hope is to use Riemannian methods to get more efficient algorithms and to get things to scale. That's what I want to talk about. So here is kind of the setup. Again, think of graph clustering if you want to think of an example, but we have some convex function f. We're optimizing over n by n matrices that are PSD and stochastic. So if you see I have two inequalities greater than 0, the bottom one means the matrix is PSD. The top one means that x is element-wise non-negative. The matrix is symmetric, so x times the all one vector being 1 means that we're stochastic or doubly stochastic here because of the symmetry. And I'll assume that the rank of the matrix we're looking for is P. So in the clustering setting, P is the number of clusters. And so if you think of n being the number of items, n can be very large. The number of clusters is P, so much smaller. So think in this talk as P being much smaller than n. And so often what one does is one drops the rank constraints and tries to solve the problem of minimizing f subject to the convex constraints. And that's what we've been doing. And as I said, it doesn't really scale. And so alternatively, what we'd like to do is to kind of exploit the fact that the matrix is rank P to solve the problem on the right, where now I'm minimizing over a matrix Y, which is n by P. So think of it as being a very tall matrix. In terms of Y, now my function is no longer convex because it's an f of YY transpose. I don't need the PSD constraint anymore, because if I look at YY transpose, that's clearly PSD, but I still need the constraint that the entries be non-negative, and the second constraint on the right is just the doubly stochastic constraint, okay? And so there's questions one asks, how can we solve the problem on the right, and when does the solution correspond to the problem on the left? And so quickly, in terms of when the solutions coincide, there's lemmas you can give. These are essentially KKT conditions. So this tells you when you get an extreme point. And you can relate the extreme point of the two problems. So by this equation too, I don't want to go into the details. The bottom line is that if you compute a y for the problem that we had on the right, one can check whether it actually solves the convex problem on the left, because the problem on the right is non-convex, and we don't know necessarily whether it solves the problem we want to, but we can check it with this lemma here. Okay, so the problem I have here on the right we've seen before. The only change is that I took the inequality constraints on the entries of YY transpose and I made them strict, because I want to use Riemannian optimization. I need my set to be open to be a manifold. And so I want to replace the constrained problem on the right with an unconstrained problem where I'm just minimizing over the manifold M sub P super N, which I've defined up there. It's the set of N by P matrices. The star below R means that all the entries are non-negative in Y. No, excuse me, they're non-zero. I mean, I don't think that's critical. But YY transpose is element-wise positive, and again, we have the stochastic, doubly stochastic constraints, so that's a manifold we want to optimize over. And if you have a manifold, we all know if I look at a point on the manifold, so manifolds typically have a metric associated with them, and one can also define the tangent space, which is just the collection of all tangent vectors at that point. For point x, we call that T sub x of the manifold M. And we saw this picture in the previous slide too. So how do you do optimization? So suppose I have some manifold M, and I want to optimize a function over it. If I want to use a first order method, I'll be taking derivatives, and of course derivatives exist on the tangent space, and so you leave the manifold, and so I need what's called a retraction to take me back to the manifold. And so one way to do this, though it's never done because it's computationally intensive, is to use the exponential map, which takes a point from the tangent space onto the manifold by taking it onto the geodesic that's in the direction of the tangent. But that's not what we'll use. We'll use the retraction, which is, as we'll see, much simpler. Okay. So here is what the steepest descent algorithm that we all know looks like if we're just doing this on a Hilbert space or Euclidean space. So you compute gradients, you set a direction, which is the negative of the gradient, you find a step size, and then you update along the step size. So if we're doing it on a manifold, so instead of the Hilbert space, we have a manifold M. Instead of the usual gradient, we'll need the Riemannian gradient, and we'll measure its norm by the norm that's induced by the inner product on the manifold itself. We need the tangent space. Again, when we find the direction, we need the Riemannian gradients. And the update, again, we just can't update because you'll go, on the tangent space, we need to retract back, and so that's the update rule through the retraction. Okay, so here's the algorithm. And, we have to, again, the colors are not coming right here. We need to, identify all the steps that we need. So here's the manifold we're looking at. Again, there's the quotient manifold too. In the interest of time, I will skip that. So we need to compute the tangent space. This is just an exercise. Here's what the tangent space is. It's the all n by p matrices that satisfy that equation. So if I'm looking at a point on the manifold y, all c of y's that satisfy this equation essentially give me the tangent space. I need the Riemannian gradient. The Riemannian gradient, the way it's defined, it's like the usual gradient. So you have your directional derivative, which is you take your function and you move it in the direction of psi of w, and you look at the change as t goes to 0. And so the Riemannian gradient is just a vector whose inner product with psi y in the inner product on the manifold gives me the directional derivative. And so in this case, again, one can compute the Riemannian gradient. Again, this is just an exercise, so it's a modification of the usual gradient, which is the capital G, and the modification has this vector alpha, which is found from that equation there. Again, this is just an exercise. And so the last thing we need is the retraction. So I would say the one thing that's not an exercise if you ever want to do Riemannian optimization is the retraction. So here's where you have to come up with it. There's no way to do it that's standard. And a retraction essentially is any mapping that to 0th and first order mimics the exponential map. So at the origin, it gives you back y, and the derivative at the origin gives you back the direction. But it's totally up to you what kind of R to design, and you typically want to do one so that the retraction can be computed efficiently. Again, I'm short on time, and so, again, as I said, the innovation in this paper really is the retraction. It's related to the DAD theorem and the Sinkhorn algorithm, if you're familiar with that. And so the expression is there. So you take your y, you add to it an all-one vector of dimension n by p. You take the gradient and you component-wise compute the exponential. And then you essentially run the Sinkhorn algorithm to make the result doubly stochastic. Again, I'm short on time. Let me just show you some numerical results. So this is a graph clustering example using Amazon Mechanical Turk. I can't go through the details, and I'm being told I have to leave. Basically, I'm showing the convex method, and I'm comparing it with the Riemannian method. So we get about 3 orders of magnitude saving in computation, and essentially the same performance. And so I'll stop here. Thank you.
We are short of time, so...
It's poster 15, if that matters.
So the next talk will be given by Tong Zhang about graphical non-convex optimization using adaptive convex relaxation.
Thanks. This is the last talk of I will finish soon. There's a lot of slides. Okay, so this is about graphical model optimization.
So I will give some motivation and background, and then I will. Huh? Oh, okay. Sorry. Let me see. Yeah, I hope now you know it's okay. Yeah, so I will give some motivations. Then I will talk a little bit about just our procedure, about non-convex optimization. Then there will be adaptive relaxation. Then I will mention about just the main theorems about what we do, and it's superior and can achieve some better rate for some conditions. Okay. So this is a graphical model. The graphical model has like variables. So we have d variables, and it has edge. Edge will be conditional dependency of the among the variables. Then the problem about Gaussian graphical model estimation is it's a Gaussian, it's joint Gaussian variable, and with a sparse conditional dependency. So you have a form about, in terms of a so-called precision matrix, theta, which is the inverse of your covariance matrix. And essentially, the matrix theta is sparse. So the goal is to estimate this sparse precision matrix. So that's basically the setup. The standard approach will, for one of the method we'll do that is doing the maximum likelihood estimate, which essentially will be here. So you have a precision matrix. This is empirical covariance, and this is a maximum likelihood. Then you put a penalty there. So here we'll consider non-convex penalty. And for the reason is it has a better performance. So example of a penalty is a convex, which for example is a L1 penalty, will be something like that. And the non-convex could be different ways, but for example, this will be a non-convex, which is truncating about this L1 by some threshold. The threshold means up to L1, then you flatten out. So this is a process. Here is a solution. The solution is by solving the adaptive convex relaxation. So the whole formula about this, with any lambda, if you fit any lambda, so this particular function will be convex. So you can solve that to your precision, and then you update lambda by using a formula. So basically, this is a procedure. The procedure will essentially converge to the things like that. So for example, you have a convex relaxation, the first one, and you have a solution to come to here, and then after that, you have another convex relaxation. You come to here. And eventually, when you do that a few times, and then you goes to the this region will have the statistical rate, and we will compute this rate in that region, which is where the solution converges to, will be leading to. Okay, so here is the main result. So of essentially this paper, the result looks at the following. So you have the convex relaxation, you repeat apply that. This is your optimal theta. Basically, this is the theta true precision matrix. And this one is your convex relaxation after L steps. Then it has this term, which is basically the inner circle you see in the previous slides. And then you have this contraction. Each time, under the conditions, you have you reduce your error about by half, and gradually this one will give you a logarithm term when you repeat that by in L. Essentially, you expand that to the 2 to the L over phi 0. And then this one basically gives you this rate. This rate comes from here. Essentially, it says that the error will be square root of S over N, which is basically the rate you will have when you look at the rate about in terms of S. So this is result. And then if you compare this result with a convex relaxation, which people do, for example, L1 norm, basically there's a slower rate about convex relaxation here, and depends on the ratio of the larger S, which is the entries of your precision matrix larger than some threshold, and entry your precision matrix smaller than some threshold. Basically, all the strong signals, which is correspond to S1, and the weaker signals correspond to S2. So when the signals are all strong, then your rate, what we compute, is coming from here. At this point, it becomes the optimal, which without log D. So here you have the log D, here without log D, and this is what you can get. So our rate is in between, depending how many signals are strong. You can get either from the same as a convex, or eventually you get a better rate. You get a better result. So depending on when the signals are strong. In addition, so you have improved the results when you have the correct support recovery. When all the signals are strong, in that case, you get strong support recovery. And then what you get is you just sign essentially the sparsity pattern matrix. When you have 1, if there's has edge, when you have a 0, no edge, then you compute that. Basically, you get instead of S here, you get this. What you actually have is this one actually should be much smaller than square root S. And for example, for the chain, when you look at the ratio of this quantity instead of typically what people use in S, you get a better result. Means that the rate will be, if you look at that, so now it's almost the same, but typically it's much smaller. So you get a better rate in terms of your sparsity pattern. It's a more precise rate, and then you get that when you have all the strong signals. Basically, that's it. So I hopefully use fewer time. Just you can go earlier. So, thank you.
We have no time for questions, so you can ask during the poster session. Thank you very much.